Yeah, I think my screen is visible, no? Yes. So we completed with K map. Today we'll discuss about introduction to the combinational circuits. Okay. So introduction to combinational circuits. Okay. Combinational circuits. Okay. So introduction to the combination circuits. Okay. So here in digital, so like in digital you have like basically digital system we already seen. So if you see the digital system, digital system. So first what we have seen, first we have seen the representation of information in digital form. No? Representation of information in digital form. Okay, digital form. So we already seen like number systems, binary codes, and conversions. Okay, this already we already seen. Okay, so example like 8421 gray code. This we already seen. Okay, and next we are seeing the Boolean algebra. Okay, Boolean algebra, logic gates, and optimization. Okay, Boolean algebra, logic gates, and optimization. Okay, and next is nothing but like we already seen the Boolean algebra. Example a dash b plus ab dash. Okay, and next is combinational circuit. Next is combinational circuits. Combinational circuits we'll see. Okay, so combinational circuits are nothing but example mux, adders, subtractors. Okay, so these are the combinational circuits. So adders, subtractors, multipliers, comparators, encoders, decoders, and parallel adders, parallel subtractors. Okay, that will come under the combinational circuits. And next you study about hmm. So next you study about the sequential circuits. So what are the sequential circuits? Like you will study about sequential circuits. So you'll study about latches, flip-flops, and registers, counters. Okay, that we will study about the sequential circuits. And next is system design. System design means with the help of combinational and sequential circuits, you can design a processor. Okay, you can design a processor. Okay, so this is system design like processor. Okay, so this is about the digital system. Okay, so we already covered this number system and Boolean algebra we already covered. So next we are going to cover the combinational circuits. Okay, so next we are going to cover the combinational circuits. Okay, one second. Yeah, so next you see, so there is a level of abstraction. Okay, so what is this level of abstraction? Level of abstraction. So level of abstraction is nothing but there are like bottom to top approach and top to bottom approach. Okay, suppose bottom to top approach means what? First if you take the low level. Okay, what is the low level? You have the low level is device level. Okay, you have a device level. What is the device level? Basically you will study about this NMOS, no? NMOS and PMOS. Here N place and here N place and this is a p substrate. Okay, p substrate, and here this is a oxide layer, and here this is gate and source, drain. Okay, so this you will study. So device level you will study. Okay, and next is circuit level. With the help of NMOS and PMOS, you can design the CMOS circuit. Okay, CMOS circuit. In this CMOS circuit, you will design the like PMOS as pull up and NMOS as pull down. Okay, NMOS as pull down, and this is nothing but basic CMOS inverter. Okay, this is nothing but CMOS circuit. Okay, this is nothing but circuit. Okay, circuit. Okay, and next level is gate. So gate means we already seen like basic gates, and gates, or gates, the NAND gates. We'll design these gates by using CMOS circuits. Okay, and next is nothing but module. Module means what? Basically, like adder circuit, combinational and sequential circuits. Okay, these are nothing but we call as modules. Okay, like if you consider adder circuit, this is nothing but module. Okay, and next you have system. System means what? You have a processor. You have a processor in this. Like this is the processor IC chip, and it consists of all these some modules. Okay, so that means you are means you can design. What is the highest level? Highest level is nothing but you have CPU. Okay, CPU. Okay, system like processor is the highest level. What is the lowest level? Lowest level is nothing but you have transistor level. Transistor, it consists of transistors and resistors. Okay, this is the lowest level. So that means suppose if you want to design, there are two approaches are there: top down approach and bottom up approach. Okay, top down approach means you need to like if you want to design a processor, you need to divide whatever these modules in whatever the parts in this processor in terms of modules. Again, you divide these modules into gates, and you can divide gates into circuits, and you can divide these circuits into devices. This is nothing but what? Top down approach. Top down approach. Okay, and bottom up approach means you need to go from bottom to top. Bottom to top. So that means device level, circuit level, gate level, module level, and system level. Okay, so this is nothing but bottom up approach. Bottom up approach. Basically, in the VLSI, we'll follow top down approach only. Okay, we'll follow the top down approach. Okay, this is nothing but level of abstraction. Okay, is it fine? The level of abstraction, do you understood? Any doubt in this? Your response? Hello?
No,
Yes?
sir.
Okay.
Yes, sir.
Yeah, yeah. Next you see. So next, if you see the um, so uh, combinational circuits and sequential circuits. Okay. So combination. So in digital circuits, there are two types are there: combinational and sequential. Okay. So digital. So if you see the digital systems or digital electronics. Okay. Digital systems. Digital systems or digital electronics. So this is divided into two parts. One is combinational circuits and sequential circuits. Okay, combinational circuit is nothing but what? The output, it depends only on the output. So this is nothing but combinational circuit and a sequential circuit. Okay, so like if you see so output is combinational circuit. Output is only depends on present input. Okay, so like suppose if you consider this this is a combinational circuit. Whatever the inputs you are giving, you are getting the output. So output is a function of what? Output is a function of only present input. Okay, this is nothing but combinational circuit. Okay, and sequential circuits are nothing but so output is depends on what? So output is depends on present input as well as and past outputs. Okay, so like if you see, so that means you have inputs and you have outputs. Okay, output will be feedback. Okay, output will be feedback through the memory. Okay, so through the memory element, output will be feedback, and it is given to some memory element. Okay, from memory element, and it is given to the input. Okay, it is given to the input. Okay, so example, so we are going to study about half adder, full adder, and ripple carry adder, and mm, um, carry lookout adder, BCD adder. Okay, these are adders. Okay, half subtractor, full subtractor, and parallel subtractor, and adder subtractor. Okay, adder subtractor, and multiplier. Okay, mux, demux, demux, and next comparator. In comparator, you will study about 1 bit and 2 bit comparator, and next code converters, code converters, and next we are going to study about encoders, decoders. All these are nothing but combinational circuits. Okay, so you are going to study about these combinational circuits, and in the sequential circuits you are going to study about latch, flip flop, and next flip flop, register. In the register, you are going to study about serial in, serial out, CISO, serial in, parallel out, SIPO, parallel in, serial out, parallel in, parallel out. Okay, and this is shift register. Shift register. Next, counter. In counter, you are going to study about asynchronous counter. That is also called as ripple counter. Okay, and synchronous counter, and you are going to study about FSM. In the FSM you are going to study by using FSM. There is Mealy and Murray is there. Mealy and Murray are going to study. In this you are going to design sequence detector by using FSM, serial adder by using FSM, serial adder by using FSM. Okay, so these are nothing but in sequential circuits. Okay, so these are going, you are going to study in the digital system. Okay, so here if you see the, so that means here if you see the combinational circuit, so that means here you have inputs and outputs. Okay, so present inputs, and the output is a function of uh, uh, present input only, but here these are inputs and these are nothing but outputs. Okay, so output will be feedback and it becomes a past outputs. Okay, so output is function of what, present input as well as past outputs, present input as well as past output. Okay, so uh, that is the difference between combinational and sequential circuits. Okay, is it fine? Any doubt in this? Your response? Yes.
No, sir.
Shall I move forward?
Yes, sir.
Okay. Yeah.
Yes, sir.
Okay. Next you see. So this is digital system, and suppose combinational versus sequential. Okay. Combinational versus sequential circuits. Okay, combination versus sequential circuits. Okay, so if you see the combination versus sequential circuits, so here if you see I'm writing like parameters, okay, and combinational circuit, combinational logic circuit, and next sequential logic circuit, sequential logic circuit. So if you see, so so that means here if you see output depends on, what, output depends on present input, whereas combinational circuit depends on present inputs at that instant of time only, at that instant of time only, okay, and here it output depends on what, present input and past outputs. Okay, what are the elementary building blocks? Okay, so the basic building blocks. Okay, the basic building blocks for combinational circuit is what, the basic building blocks of combinational circuits are logic gates, okay, and here the basic building blocks of sequential circuit is flip flops, okay, and memory. Okay, if you consider the memory, so memory, for combinational circuit memory is not necessary. Okay, memory is not necessary, and here memory is necessary, memory is required for the sequential circuit. Okay, and coming to the clock this is independent of the clock. Okay, independent of the clock, and here this use clock for triggering, This use clock for triggering. Basically, we'll use in the flip flop. Okay, triggering the flip flop. Okay, flip flops are nothing but edge trigger, no? Okay. Next, feedback. Feedback. If you see, feedback not present, feedback not present, and feedback present. Feedback present. Okay, and processing speed. If you see the processing speed, it is fast. Why it is fast? So whatever the inputs you are giving, that change in the inputs, you are getting the outputs. Okay, so there is no feedback. Okay, the output will be not feedback, so it is fast. Okay, and this is slow. So why? Because the output will be again feedback to the input, and again you are getting the outputs. Okay, so there is a feedback network, and it should pass through the memory element. Okay, so that's why this is slow. Okay, so this is fast and this is slow. Examples we already seen. So what are those? Half adder, encoder, okay, encoder, decoder, okay, decoder, mux, demux. This we already seen. Okay, and next here flip flops, shift registers, and counters, FSMs. Okay, finite state machines. Okay, FSMs. Okay, FSM means it is having finite number of states. That's why we call as FSM. Okay, so this is about the difference between combinational and sequential. Yeah, any doubt in this? Give response. Shall I move forward?
Yes, sir.
Hello.
Yes, sir.
Okay. Next, design procedure of combinational circuits. So if you see the design procedure, design procedure of combinational circuit. Design procedure of combinational circuit. Okay, so if you see the design procedure of combinational circuit, so here step one. So step one, uh, from the specification of circuit, identify the number of inputs and outputs. Okay, from the from the specification from the specification of the circuit, identify identify the number of inputs and outputs. Okay, and step 2. So what is step 2? You need to find out number of inputs and outputs. Okay, and derive the truth table. Derive the truth table. Derive the truth table that defines the relationship between input and output. That defines the There should be relationship between input and output, no? So from the truth table you will get the relationship between input and output. Okay, and next step 3, obtain the simplified boolean function for each output using k-map. Okay, obtain the simplified function simplified function for each output using k-map, Karnaugh map. Okay, k-map we already seen, no? And step 4, draw the circuit using logic gates. Draw the circuit using logic gates. Okay, circuit using logic gates. Okay, so this is the procedure. First you need to find out the number of inputs and number of outputs, and next derive the truth table by using that defines the input and output, and obtain the simplified function for each of output using k-map, and draw the circuit using logic gates. Okay, so these are the steps. Okay, so just we will design some combinational circuits based on this. Okay, it is fine now. Do you understood these steps? Okay. Hello.
Yes, sir.
Okay. Next you see. So designing of this combination circuit. First problem is how to design the combination circuit. The minimal function. The minimal function. The minimal function that can detect divisible by 2, divisible by 2, that should be divisible by 2 with 8421 BCD code, 8421 BCD code. So let us take the inputs are BCD code D8, D4, D2, D1. Okay, D8, D4, D2, D1 is given by so he's asking the output. Okay, so first, what is the first step? You need to find out the what is the first step? You need to find out the number of inputs and outputs. Okay, so if you see the inputs, how many inputs are there? By seeing this, he given that BCD code. BCD code means you have D8, D4, D2, D1. 4 inputs are there. What is the output? Output, you have only one output. Okay, so this is the first step. Okay, after that, to get the relationship between input and output, you need to draw the truth table. Okay, so what is the truth table? So that means what is the range of BCD? 0 to 9 only, no? So I am writing the inputs D8, D4, D2 and D1, and here this is the output 8421 code. Okay, this is the output Y. Okay, so if you see, so 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 and 0 double 1 0. Okay, 0 triple 1 1 0 0 1 0 0 and 1 0 0 1. Okay, from 1 0 1 0 to 1 1 1 1, those are nothing but what? Those are invalid. Okay, actually those are nothing but invalid, no? So that means based on my problem, so what he given, it should be divisible by 2, no? So that means 0 is divisible by 2, so I can write 1. Okay, 1 is not divisible by 2, I can write 0. Okay, again 2 is divisible by 2, so 2 is divisible by 2. Okay, that is, so 0 0 1 0 is 2, so that is divisible by 2, so I can write 1. And this is 3 is not divisible. Okay, and 4, so 4 is not 4 is divisible by 2. Okay, I can write 1. And 5 is not divisible, I can write 0. 6 is divisible by 2, so I can write 1. And 7 is not divisible, I can write 0. 8 is divisible by 2, I can write 1. And 9 is not divisible, I can write 0. And 10 is divisible. 10 means, so from 10 to 15, I can consider as don't case. Okay. Suppose, so you can write the minterms. What are the minterms? So summation of m of, what are the minterms? 0, 2, 4, 6, 8. That's it, no? 8. 8 plus don't cares of. Don't cares. What are the don't cares? From 10 to 15 are nothing but don't cares. Okay. So I got the relationship between input and output. So what is the next step? So next step means you need to draw the K map and you need to get the logic expression. Okay. So this is by seeing this is 4 variable K map. So 4 variable K map means this is 16 cells are there. 16 cells are there. 4 variable K map. So 16 cells will be there. So 16 cells. What are the inputs? D8, D4, D2, D1. Okay. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. Okay. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. Okay, so I need to group, so that means wherever these minterms are there, I need to write 1 0 2 4 6 8 and from 10 to 10 11 12 13 14 15 are nothing but don't cares. Okay, 0 and okay, yes. So depending on the possibility, I can consider don't cares as what? 0 or 1, no? So I can consider don't cares as 0 or 1. So here what I am doing, this don't care I am considering as 1. Okay, these two don't cares I am considering as 0. Okay, this also I am considering as 1. So if I consider this don't care as 1, this one corner grouping is allowed. Okay, this one makes one octet, no? So octet is nothing but grouping of 8 ones. Okay, so octet will eliminate how many variables? It will eliminate 3 variables. So that means if you take the common term, so 0 is common. Here also 0 is common. So that means I can write y equal to what? D1 bar. Y equal to D1 bar. So I got the logic expression. Next you draw the logic diagram. So what is the logic diagram? So just inverter. So this is D1, and here you are getting y equal to d1 bar. Okay, so like this you can design, that is divisible by 2. Okay, divisible by 2. Okay, so your task is you need to design the same circuit that is divisible by 3. That should be divisible by 3. Okay, so same truth table you can write, but wherever the 3, so multiples of 3 are there, that you need to take as 1, and you need to take the min terms, and you need to draw the k map. Okay, and get the logic expression and draw the logic diagram. Okay, that is your task. Okay, so that is your task. Okay, so did you understood your task? Did you understood this one? Just give response.
Yes, yes.
Yeah. So next, if you see the combinational circuit example, suppose any logic diagram is given, combinational circuit example. Okay, combinational circuit example. If you see, okay, so so if you see combinational circuit example, suppose this is one combinational circuit. So this is one combinational circuit. Okay, so combinational circuit is given. I want to get the logic expression. Okay, how to get the logic expression? Suppose like so if you consider, so this is nothing but what, so find the, so like he will ask find the output of this given expression. Okay, so I know that here what is this, this is nothing but AB. Okay, and this is nothing but what, AB bar, no, this is so this is AB bar, this is AND gate. Okay, this is AND gate. By seeing this I can understand that this is NAND gate. Okay, so let us consider AB equal to what, let us consider X. So AB bar equal to what, we will get X bar. Okay, AB bar equal to X bar. So here what you will get, this is nothing but OR gate, X plus X bar. Okay, X plus X bar, that is equal to what, 1. Okay, so that means here you are getting what, 1 is one input, and other input is what, C. Okay, other input is C. Okay, so here what you are getting, that means C XOR of 1. Okay, C XOR of 1 means there is a properties of XOR gate. So you know that A XOR B equal to what, A bar B plus A B bar, no, A bar B plus A B bar. In place of B, suppose if you have 1. Okay, so that means A bar and 1 plus A into 1 bar means what, 0. Okay, so this is nothing but what, A bar you are getting. Okay, so that means this is equal to what, C bar. Okay, so this value is what, this input is C bar you are getting. Okay, and next this input is connected with a bubble. Okay, so this input is connected with a bubble. So this is nothing but XOR gate, no. So one more property of XOR gate is there. So this is nothing but so here you are getting what you are giving through the bubble means D bar you are getting. Okay. So A XOR A bar. Okay. This is equal to what A bar. Just you expand A bar A bar A bar. Okay. A bar in place of B bar you have A bar. Okay. Plus A and A bar whole bar. Okay, a bar whole bar. Okay, so this is nothing but a bar plus a bar whole bar equal to a. Okay, so this is nothing but what a bar plus a. From Boolean algebra we already seen a and a equal to what a and law. Okay, so from R law a bar or a equal to what 1. Okay, so that means here you are getting like d xr of d bar. Okay, equal to what 1. Okay, d xr d bar equal to 1. So this is one input 1, and here y equal to what y equal to again c bar x nor of 1, c bar x nor of 1. Okay, so for NOR gate you know that a x nor b, what is the expression? A bar b bar plus ab, a bar b bar plus ab. Okay, so this you can write as in place of so what you have c bar you have. Okay, so if you compare with c bar x nor of 1. Okay, and in place of b you have 1. Okay, so that means c bar whole bar and 1 bar plus c bar and 1. Okay, so this is equal to what c bar whole bar, complement of complement is true form, c and 1 bar is 0 plus c bar and 1 is c bar. Okay, so anyway this is 0 only, 0 plus c bar. Okay, 0 plus c bar is nothing but what c bar you are getting. So that means y equal to what y equal to you are getting c bar, y equal to c bar you are getting. Okay, so like this you need to analyze any logic equation is given like this. You need any combinational circuit like this in terms of gates they given, you need to find out like this. Okay, is it fine? Do you understood? Any doubt in this? Any queries? Your response? Yes. Shall I move forward?
Yes, sir.
Okay, so next you see. So next redundancy of gate. Okay, redundancy of gate. What is this redundancy of gate? We'll see. Redundant gate. So if you see the redundant gate, suppose like they given, like this. So three NAND gates. Okay, so this is gate 1, gate 2, gate 3, and gate 4. Okay, he given the inputs A, B bar, C, and this is A bar, B bar, and next C, and this is A, B, and next C bar. Okay, he's asking what is the redundant gate in the given combination circuit. Okay, so what is the redundant gate? Redundant gate in the given combinational circuit. Okay, so how to do? Suppose here if you see, so this is NAND gate, no? So NAND gate means what? A B bar C whole bar. Okay, A B bar C whole bar. So if you apply De Morgan's law, what you are getting? A bar, okay, plus B bar whole bar, complement of complement is true form, plus C bar. Okay, and next if you see, so this is nothing but what? A bar B bar C whole bar. Okay, A bar, B bar, C whole bar. So if you write in terms of if you apply De Morgan's law, if you write so complement of complement is true form. So this is A, and here also complement of complement is true form B plus C bar. Okay, and next and this one if you see, so this one A B C bar. Okay, A B C bar whole bar. So if you apply De Morgan's law, A or B, A bar or B bar or C bar whole bar is nothing but C. Okay, C bar whole bar equal to C. Okay, so that means you need to identify. So that means here what is the redundant gate means you need to identify like sorry, change the color. See here. Suppose uh, suppose A bar is there. So A bar is there in this gate. Okay, A bar is there in this gate, and B is there in this gate. Okay, B a variable is there in this gate, and C is there in this gate. Okay, so that means all the variables or all the literals, whatever the literals are there, that are present in the remaining expression. Okay, so remaining expression. So that means this is the redundant gate. This is redundant gate. Okay, so this is the redundant gate. And suppose if you compare this one and this one, suppose A is there, A is not there in any of the equations. See here, if you consider A is not there in this expression and A is not there in this expression. Okay, anyway B is there. Okay, B is there in this expression, C bar is there, but A is not there. So that means this is compulsory present in my expression. This gate should be compulsory present. Okay, suppose if you consider this gate is nothing but if you consider B bar is not there in any of the expression. Okay, and C also not there in any of the expression. This should be compulsory present in my expression. Okay, so now what is the redundant gate? So gate 1 is the redundant gate. Gate 1 is the redundant gate. Okay, so like this. Okay, yeah. Suppose if you take one more example. mm, mm, okay, suppose like what is the redundant gate? So this is gate 1, gate 2, and gate 3, and gate 4. Okay, so here let us take the variables x, y bar, z bar. Okay, y bar, z bar, and x bar, y bar, z, and x bar, y, z. Okay, so this is a NAND gate. Okay, NAND gate means what? Here if you see x, y bar, z bar, whole bar. Okay, if you apply De Morgan's law, what you are getting? X complement of complement is to true form, you are getting y plus z. Okay, and here if you see, so x bar, y bar, z, x bar, y bar, z, no, x bar, y bar, z whole bar. Okay, so this is nothing but what you are getting? Complement of complement is true form, x plus y plus z bar you are getting. And here if you see, so this is x bar, y, z whole bar. Okay, so if you apply De Morgan's law, so complement of complement is true form, so x, y bar plus z bar. Okay, so so if you see, so if you like this is y, what is the redundant gate? Okay, so what is the redundant gate means what you need to do? Here you need to like find out. mm, so so if you see this one, x bar, wherever x bar is included, x bar is not included, no? So x bar is anywhere common in this any expression. So x bar is not common. X bar is not common. Okay. So x bar is not common means this gate is not redundant. This gate should be compulsory present in my expression. Okay. And if you see this gate, x is there in this expression. Y bar is there. Y bar is not there. Okay. So y bar is not there means this is compulsory present in my expression. Okay. If you consider this one, so x is there in this expression, and y is there in this expression. Okay, this is y. Okay, and z bar is covered in this expression. Okay, so all three terms are covered in this expression. This is my redundant gate. So what is my redundant gate? Redundant gate. So redundant gate is nothing but gate 2. Gate 2 is my redundant gate. Okay, so like this you need to find out the redundant gate. Okay, similarly one more example we will see. Suppose like the last example, suppose here now I am considering OR gate. So this is nothing but A, B bar, C. Okay, this is nothing but A, B, C. Okay, so this is nothing but what? A bar, B bar, C bar. Okay, A bar, B bar, C bar. So here if you see, so that means here what you are getting? A or B bar or C. Okay, so this is first gate. Okay, first gate, second gate, third gate, and fourth gate. Okay, so this is nothing but what? A or B or C. A or B or C. So this is nothing but A bar or B bar or C bar. Okay, A bar or B bar or C bar. Okay, so here if you see, so I want to find out the redundant gate. No, so here I am checking so from starting of the gate I'm checking. So A is repeated. Here A is repeated. B bar is repeated here. Okay, and C is repeated. All the three terms are repeated in the first gate. So this is the redundant gate. Okay, so if you check this gate, A is repeated. Okay, A is repeated, but B is not there. Okay, so B is not there in any of the expression. So this is nothing. This is not my redundant gate. So it should compulsory present in my expression. Okay, and if you consider this one, A bar is also not repeated. Okay, A bar is also not repeated. So this also compulsory consist in my expression. So what is the redundant gate? So redundant gate is nothing but redundant gate is nothing but gate 1. Gate 1 is redundant gate. Okay, so like this you need to find out the redundant gate. Okay, so this is about today's session. So today's session we first what we have seen the introduction to the combinational circuit, that is digital systems, first representation of information in binary form, like number system, binary code conversions, binary codes that we have seen, and Boolean algebra, Boolean laws, and their optimization, realization the logic gates by using NAND gate and NOR gate we have seen, combinational circuits, sequential circuits, and system design. Okay, so combinational circuits like mux, adders, subtractors, these combinational circuits, sequential circuits like counters. Okay, system design means SoC, system on chip, or processor, that is nothing but total system design. Okay, with the help of this combinational and sequential we will design the system. Okay, so we already seen the hierarchy. Hierarchy means top down approach and bottom up approach. So first it will start from device. Device will, with the help of devices, with the combination of devices will design the circuits. With the combination of circuits we will design the gates. With the combination of gates we will design the module, like combination and sequential circuits like adder, mux, and with the combination of modules we will design the system. Okay, so this is bottom up approach, and top down approach means system, module, gate, circuit, and devices. Okay, so basically in the VLSI will follow the top down approach only, not bottom up approach, top down approach. So we'll take the some specifications, and we'll write the program by using some RTL design. Okay, we'll test or we'll verify that circuit, and we'll give it to the backend part. Backend will do some chip design. Okay, so that is level of abstraction. So digital systems are divided into two types of combinational and sequential circuits. So the output depends only on the input. Your output depends only on the input, as well as present input as well as past outputs. We've seen some combinational circuits. These combinational circuits we are going to study. Okay. and also the sequential circuits these are going to study. Okay, so what is the difference between combinational versus sequential? Okay, so related to the parameter, related to output, elementary building block, memory, clock, feedback, processing speed, examples, this we already seen. Okay, and we already seen the how to design the combinational circuits, steps for designing combinational circuits, and we took one example like divisible by 2. So based on this design steps only, first I found out the number of inputs and number of outputs, and I drawn the K map. I got the minterms, okay, standard sum of products, SSOP. From this, I drawn the K map and I got the expression. With the logic expression, I draw the logic circuit, okay. And this is suppose any circuit is given in terms of logic gates. So how to minimize or how to get the output, okay. This is one example. Next, we have seen the redundancy of gates. So first you need to draw the logic expression for all the gates, outputs of the gates, and then need to see the variables. Suppose for one gate, all variables are repeated or common in other gates, that becomes the redundant gate. Okay, we have seen the three examples. Okay, so this is about today's session. Okay.